In this installment, we are going to introduce rotational dynamics. And I selected this picture below as a very famous example of one aspect of rotational dynamics called the conservation of angular momentum, in which we have a figure skater who is spinning with her arms out. And when she brings them in close, her rotational speed, her omega, will increase. And then when she straightens them out and extends them again, she will slow down. And when she brings them in, she will speed up. And she can go back and forth like this, and the speed will change. And what we realize is that in understanding the natural world, the physical universe, that there are rules and laws that govern rotational motion. So when we look at rotational motion, we could ask questions like we've asked before. Why do objects change their rotational motion? What are the concepts that govern the rotational motion? And what are the rules and principles that govern? And in an international context, how does the physics of rotation affect our daily lives? So as we've seen previously in the course, we map out conceptually where we are situated. So we know that mechanics has two major aspects, kinematics and dynamics, where kinematics is descriptive and dynamics is the why behind everything. Well, we've also seen that kinematics can be broken down into linear kinematics, and we've also seen rotational kinematics, where in linear dynamics we have concepts of x and v and a, and in rotational we have theta and omega and alpha. And those kinematics also can be used to describe objects in simple harmonic motion. Now, when it comes to the why, the very interesting part, we have the two omnibus rules that govern the entire universe, that drive virtually everything, and that's the conservation of momentum and the conservation of energy. Now, what you may not be surprised then is that there is the linear momentum and there is angular momentum. So the case of the skater is angular momentum. So we have linear momentum P and we have angular momentum L, capital L. And throughout this lesson, this introduction, you'll see that the blue are the rotational concepts and the orange or the rust are the linear concepts. When it comes to the conservation of energy, there's translational kinetic energy. That is in a straight line. And there is rotational kinetic energy, which is in a circular path. And we also have these supporting concepts. The supporting concepts are forces for translational kinetic energy and linear motion. And I didn't change my color here. This should be blue, and this should say torque. And torque is about rotation. So in this case, torque is rotational force. So whereas forces, capital F, bring about changes in linear velocity, and we observed the effects of forces in linear motion, torques bring about changes in rotational kinetic energy or rotational momentum. So let's meet the formulae. In physics, this is our family, the formulae. So this is from Mr. H, and this is from the AP. And we'll make a comparison afterward, but you'll see why it's more useful to look at the ones I'm giving you first. So when we have a concept, the first concept we have is something new. And what we learned when we learned about inertia previously is that inertia depends only on the mass. Inertia depends only on the mass. With rotational motion, it depends on the mass and where that mass is, the distribution of that mass. So we see there's mr squared, whereas inertia is just the mass. Rotational inertia is mass times the distance of that mass squared. And so this is our mass inertia concept. So, of course, we recognize our friend momentum. P equals mv. And similarly, the angular momentum, L, is equal to the equivalent of mass, the rotational inertia, times the angular velocity. And this one has a special name, the angular momentum. And we can look at the change in momentum. Delta P is m delta v. So, of course, the change in rotational momentum will be due to a change in the rotational velocity. And we can look at the translational kinetic energy. The change in kinetic energy is 1/2 m times the change in velocity squared. Well, the change in rotational kinetic energy is going to be equal to the mass times the change in angular velocity squared. So you notice that we're just changing. Whenever we see m, we're changing it for I. When we have v, we're changing it for omega. And in linear systems, we know that the definition of force is the rate of change of momentum. Well, the net torque that brings about accelerations in rotational systems is the rate of change of angular momentum. So if something is spinning at a constant speed, it has an angular momentum. And if we provide a force to it, well, that velocity, that angular velocity, may increase, and therefore we have a change in a rotational acceleration. And looking at the change in momentum, which is m delta v over delta t, well, then we have, it is the equivalent of m in the inertia times the change in rotational velocity, change in time. And ma becomes I alpha. Again, the inertial component times the linear acceleration, the inertial component times the rotational acceleration. So every one of these formulae, there is an analog where we're substituting in linear and rotational motions. Now this one I will call the Rosetta Stone, which allows us to connect these two worlds, the linear and the rotational. And what these mean we'll explain later, but this is the Rosetta Stone. And we have Newton's second law. This is the linear Newton's second law, and this is the rotation. Newton's law of rotation, second law of rotation. So we've got the net force, net torque. Sum of the forces, sum of the torques. Ma, I alpha. And so those are our formulas. And I find it's usually hidden to us, but this parallel construction of the formulas is I find very, very helpful. Whenever we want to apply a concept in a rotational system, we can think about it in terms of its analog in the linear system. So now let's try and identify the formulae that exist that I listed here and showed you versus what the AP gives you. Now this here is a reworking of this. And as we go down the list, we have the equivalent here. We have the Rosetta Stone. We have the definition of angular momentum. And you'll notice this delta L is T delta T. And you can see then that that is here. If you rearrange this, you get the change of momentum as the torque times the change in. Again, I don't think this is a useful version of the formula. It's much easier to make this parallel construct. And we have the kinetic energy is equal to 1/2 I omega squared, which you have here. And that is everything. So you can see that there is and of course in the linear realm, let's just find the linear realm here. We have P equals mv, and we have rearranging this. We have this, and we have the kinetic energy. And so what we are missing is some of the connections down here. Let me change that. The connections down here and this. But laying them out side by side I find to be very, very helpful. Helped me when I was learning, and it helps me even in my thought process today.